I'm going to talk about refinement types today, and specifically Liquid Haskell. So, who here doesn't know what is refinement types? Doesn't? Okay. Okay, somebody will learn something. Okay, so this is the standard example of refinement types. So refinement types essentially refine types with logical predicates. And the standard example that we have for refinement types is list indexing, right? So we have the Haskell type of list indexing that says, give me as input a list, an index, and I'm going to give you back the ith element of the list. And we use refinement types to encode properties that are not by default encoded by the type system. And in this standard example of refinement types, we use refinement types to encode like safe indexing. So we name the first argument, the list argument, we name it x's. We name the index I, and we use this logical predicate to say that the index I can be between 0 and the length of the list. And this is the standard example, and the refinement type checker that I am going to show is Liquid Haskell. And what is cool is that list indexing and other built-in operators come by default in Haskell using refinement types. So let me do a demo. Okay, this is too small. Okay, let me try here. So Liquid Haskell is a GHC plugin for Haskell, which means that you can use your standard build procedure, and you say, like, when you build your project, you use the plugin Liquid Haskell. So now every time I am saving my project, I have the plugin of Liquid Haskell running on the background, right? So here I have my light example, and I have as an input a list, x's, an index I, and as we saw, if I try to index x's with I, I'm getting a liquid type error, and we are lucky because we are still in the light case, and in this light case the type errors make sense, at least to me. And it says like, you gave me I expected something that is greater than or equal to 0. So to make this I greater than or equal to 0 when I am doing indexing, what I can do is I say if I is what you ask me, right, greater than or equal to 0, then go on and do the indexing, else nothing. Okay, and I have a Haskell error that says, okay, you gave me an index. Okay, so we made the step, the error changed, and now the error says you gave me I want something that is less than the length of the list. So I can say, okay, I should be greater than or equal to 0, and also I should be less than the length of the list, and we are all good, right? So we have safe indexing is checked by Liquid Haskell, and then we're going to check the next very common error, which is division by 0, right? So here I index my list of integers, and I got back an integer. So what I can say is I am going to use this integer to divide 42 by this. And the moment I hit save, Liquid Haskell run on the back, and it says, you give me something A, but you use this as the second argument of the division, and I want you to prove me that what I divided with is different than 0. Okay, so if we want, we could have another runtime check, and Liquid Haskell will understand it, but we're going to do something else. We are going to specify, we're going to use a liquid type for the test. So I use the special comment to declare liquid types, and I'm going to say that all the elements here in the list are different than 0, because basically I'm dividing with a random element from the list, right? So I can say that the elements of the list are values v that are integers, and also this value is different than 0. And we're all good because I got something from a collection that is different than 0. Okay, and since we put the refinement type, we can have also like these dependent refinement types, and we can say that my input list, I'm going to name it x's, and then my int xi is an integer where I is greater than or equal to 0, and also I is less than the length of the list. All good. So, but like with what I did now, I can, like, I don't need the runtime check anymore, right? You can see that. And this is like I was discussing yesterday with somebody about this. This is like a very nice case that you see that refinement types can be used for verification, but also they can be used to remove runtime check. So if you prove properties, you don't need to check them at runtime anymore. Yeah, this is the standard example of refinement types, but what I have been pushing is this, what I call deep verification, that is something that I really like and has all these ideas that we we show already at some talks. It's like carry hard isomorphism, like you have programs, but they are actually proofs. And like with this deep verification, what you do is actually you run proofs as Haskell programs. And these proofs prove properties that you declare using refinement types. So here I am declaring the right identity property, and I am saying that for all list x's, if I append x's to the empty list, then I get back x's, the right identity of append on list, and undefined proves everything, which is fine. But I want to do a proper proof, and to prove this property, I am going to do a proof by induction. So I have my base case, unit, fine, and my inductive case, where my list is a cons, is like an inductive call. And Liquid Haskell says line 12, I cannot prove it, and this is like, if you do this kind of proofs, then the error messages you should not look at them, but you should look at the line that says line 12, I cannot prove it. And so we are importing this library of proof combinators that have some combinators that are Haskell functions that let you do proofs, and you can do the proof by rewriting, right? You can say x's, where is the empty list, append by the empty list is equal to the empty list, and this concludes my proof. And this is a good proof by rewriting. I'm just doing the rewriting steps, right? And then I, like, the error moved to line 13. So my base case is fine. Let's do the inductive case, which is a little bit more verbose, but it's the same. We go by rewriting. So now my x's is x con x's, append to the empty list. This is equal to x's append to the empty list. And now I can use a right identity to say that this is, Copilot is very good, but it doesn't know alignment. And this concludes the proof, right? Okay, all good. That's a Haskell code that is also proof, which is very cool, but it is very verbose. Because we are opening up steps, we are doing rewriting, and this is very verbose, and we have a tactic in Liquid Haskell to automate this, and this tactic is called PLE, proof by logical evaluation. So this is comment. If I put the star, I activate, like I tell Liquid Haskell, take that into account, it parses whatever is inside. All right, so proof by logical evaluation means that all the rewriting steps are done for you. So we can remove like everything that is not calling external things. So the only external thing here is right identity. So I'm putting right identity, and the other steps are just rewriting, and PLE is going to figure them out. So this is my inductive proof of right identity, right? Cool. Let's do one more now that we have PLE. And it's very easy. This is associativity. I have 3 input lists, x's, y's, and z's. And I say that if I append first y's and z's, this is equal to if I append first x's and y's, right? And the proof is by induction. on axis. So I say if axis is the empty list, then fine. If it is a cons, then I do induction and it's fine, right? Cool. Okay, let's do the difficult one now. Distributivity, which says I have x's and y's. If I reverse x's append y's, it is the same as reversing y's and then reversing x's. Okay, so let's try to prove this as with append. Let's try proof by induction. Oof. No, it's fine. We will do it without this. Proof by induction says I am just doing distributivity x's y's. Okay. Okay, and this is not enough, right? Oof. This is not enough. Should we try to do this? We can try to do it as we did at the beginning. If somebody knows the proof, they can say. No? Somebody has done this proof before? No, okay. So let's try to do the base case then. So the base case says reverse x's is my empty list, append y's, right? And I want to reach a state that this is equal to reverse y's, append reverse the empty list. And I get the error at line 59 because it says I cannot go from here to here. Okay, I know that this is equal to reverse x's because if I append the empty list with something, it's fine, but I want to append on the right my empty list. And this is a difficult thing, but we are fine because we proved at the beginning that if I append somewhere on the right the empty list, we're good, right? But I need to call the right identity. So I will come here and I tell it that to go from here to here, you need to do the right identity on reverse y's. And now my error went to line 62, which means that the base case is fine, right? So I need some time to call things on the right. Okay, and distributivity, I think I have time to do it explicitly. Okay, distributivity says, let's start from the left-hand side. I am reverse this, and this is equal. Okay, I have a lot of time because Copilot helps me. Okay, it calls distributivity. And now, if I call distributivity, I open it up. And I open it up, but I have my parentheses here. And I want to put my parentheses on the other hand side, right? So I call associativity of all this, which means that my parentheses leave from here, they go on the other side, and I can now prove that this is equal. I don't need that. And then figure it out yourself. Ta-dun! All good. Cool? Yeah, there is some automation. But still, so we said you have PLE, which means that with PLE you only need things, essentially you need the things that come after the question mark. And PLE in this kind of normal proofs works quite well, so I can just remove all the equational steps and keep only the things that are after my question mark. So I keep this and I keep the associativity. And this should still go through. Yes, all good. But the last thing that we have, like somewhat more experimentally in Liquid Haskell, is a rewriting system. And so here, like maybe you know that you want to use right identity, but you don't know exactly with what. So you can remove that, and you can say, I have it here again. I was not using it. That is why it was not going through. You can say prove distributivity and use as rewrite rules associativity and right identity. So you can remove that. And the cool thing about this rewrite is that Liquid Haskell is going to try to figure out the arguments, which happens in like most theorem provers. But like maybe if you have too many things, maybe it's going to get like too heavy for it. Okay, good. Yes, like I encourage you to play with Liquid Haskell, especially this theorem proving that I quite like. But let me go back to the slides and try to explain what happened here. So we have a refinement type checker. Essentially, they take as input a program and a property. And the whole idea of refinement types is that they use a set of rules to generate a logical condition, and they give this logical condition to the SMT. And if the SMT decides that it's valid, then it says that the program satisfies the properties. So in our example, the original example, the property we used was safe indexing. So the logical condition that was generating was from whatever information you have in your program, can you imply the logical condition? So at the beginning, the information was true at the first example, so it couldn't. And then we added the logical we added the if. So like essentially the SMT should prove that from like the I within bounds, it should imply I within bounds, which was identity, and it said yes. Right? So this is the first nice feature of refinement types, and it is that it is case sensitive. So it takes into account the branching. And the other nice feature that we saw is that the refinement verification with refinement types is this type-based. So we saw that if you have a list, you can refine all elements of the list, and you can say that they are all good divisor operators. And this is very important because you can describe elements of collection without using this for all qualification. And the for all qualification is not very good for the SMT solvers, because if you start using for all, then verification with SMTs may be unpredictable, so it may diverge. And this is a big problem, like Rustan Leinon, who is the Daphne developer who has played a lot with SMTs, describes this unpredictability of SMTs as the butterfly effect. And it is bad because if you change something at one point of your program, maybe things change at the other point of your program. So with refinement types of Liquid Haskell, we just restrain verification. We just restrain the logical queries that we generate to decidable theories, right? So what can we prove using the decidable theories? And the trick there that we saw is that before we send things to the SMT, we use this layer. So we use that we have PLE, proof by logical evaluation. We have a REST that we use to do some rewriting. But like we do all this pre-processing before the SMT to ensure that the SMT queries are predictable and decidable. And so these are some features of the refinement type checker. Decidability type-based SMT automated are the very important ones. And the last is that it is language integrated. So as I mentioned, Liquid Haskell is a GHC plugin, so it is part of the compiler, which means that you can use it to take advantage all the benefits that the compiler gives you, which is like editor integration. You can use it for cloud testing, and you just put it as part of your compile project. So these are the features, the main features of the refinement types, the main design features of refinement types. And all these features make refinement types, like they are designed to be practical. They are designed with all these features in mind. Okay, so assuming that you believe me that refinement types are designed to be a practical verification technology, in the rest of the talk I am going to explain like if the refinement types are expressive, if they are general, and if they are sound. Okay, so let's talk about expressiveness. So we show like there are two modes of Liquid Haskell. There is this light verification that everything is decidable. The logic that we send to the SMT is like constrained very concretely to this linear arithmetic interpreted function data types. And this is enough to do all this inbound indexing, to propagate properties using the uninterpreted functions. And they are direct to express, yes, safe indexing, division by zero, which are the standard example. But also, like if you push it a little bit, you can also express recursive properties like sortedness. And now, like what I like to work on is this, like pushing the expressiveness of refinement types to other domain-specific properties. And an area that I really like working is this secure web applications. And the reason why I like verifying this area is mostly because the properties in the security domains are very well defined. And I'm going to tell you an example of this very well-defined property. And the idea is that we have programs. The program manipulate data from a database. And these data that are stored in the database can have different policies. So they can be secret, which is red, or they can be public, which is green, right? And a property that people want to have when they interact with these secure applications is what they call non-interference. That different labels, secret and public labels, cannot interfere with each other. And like a concrete example is that if like I run a program and I have public access, the program cannot depend on data that are secret, right? So LWeb is an application that actually relies on a Haskell library about non-interference that's called LIO, and it's a very good, so LIO is a very good library because it basically uses IO as a security monad to make sure that nothing leaks. And what we did is on top of LIO, we developed LWeb that also have access to a database. And what we did at POP19 paper is we used refinement types on a model of LWeb to prove non-interference. And exactly the theorem we proved is that execution preserves low view. And the idea for the proof is that we have the program, it manipulates data, and if we erase all the protected data, so if we use this erasure function that removes everything that is secret, the value should not change, right? So if my access is public and I run this function, the value, the execution of the program should be the same as if I erase, like replace with whole all my private data. And the theorem we proved is called non-interference. It says for each label L, for its two programs P1 and P2, if the erasure or low view of the programs is the same before, the erasure or low view of the program should be the same after. And this is like this deep property, like associativity, distributivity that we proved before. And we use Liquid Haskell to prove this property. Of course, the proof was a little bit bigger. It was 5.5K lines of code. And but like this was the first example that saw that like you can actually use Liquid Haskell, this like refinement type checker to prove like real properties, real meta properties, and actually like we found out 2 bugs on the original implementation, which like always when you verify something, like finding bugs is a good thing. So yes, this is the first, like I think like this web secure applications is an area, a domain-specific area that there are many, many properties that you can prove, but also we have used Liquid Haskell on other specific domain applications like resource users or distributed applications. And these are examples to show that if you put a lot of effort, like 5K lines of code, you can actually use refinement type to prove these domain-specific sophisticated properties. But if you want to use it like on your project right now to prove like light properties, decidable properties like safe indexing, it is there, it is ready, you can use it. Yes, but the conclusion on the expressive side is that if you want to put the effort, you can go and prove, you can use it as a general theorem prover to prove fancy properties. And the next topic is it general? Is the technology of refinement types general enough? So refinement types actually started from OCaml. And when we ported it to Haskell, the challenge there is how do you deal with laziness, because actually the refinement types of ML were unsound under laziness, and we implemented a termination checker to make sure that everything is terminating, so evaluation order is not important. Yes, but they started from ML, and now Liquid Haskell has implemented refinement types for Haskell, and this quite works. Then last year or some years ago, there is another liquid type checker for Rust that is called Flux, and I think this is very cool too. And then there is Liquid Java that add refinement type specifications in Java program, and of course there is I think since you said most of people here are Scala programmers, there is from the EPFL, Kundkat, I think more than Martin, work on a refinement type checker for Scala that is called Stainless. And yes, this works too. You should try it. And there are every year there are more refinement types for X programming language. And the cool thing is that the principles of a development of refinement type system for X language are general if you stay in the core of the language. But of course, every language has their own features. Yes, Haskell had laziness, Rust has all these memory fancy operations. So if you want to deal with these specific properties, you need to adjust the technology of the refinement type development, and you need to put some thinking again onto it. But if you want a core calculus, this refinement types tutorial is going to give you step by step how to implement your own refinement type checker. Yes, and with this, I could conclude that refinement types are also general in the sense that they can be developed for various programming languages. And the next interesting question is, are refinement types sound? Right? What is sound? We say that a type system is sound when it only accepts programs that cannot get stuck. That is the textbook definition of soundness. Right? And we can put it in math, and we say if the expression E, a refinement type checks with some type T, and E takes some evaluation step and goes to some expression E, then either E is a value or E is going to take one more step. Right? The cool thing is that this is a theorem. It's math, so we can make it into a refinement type in Liquid Haskell. So this is how you express soundness in Liquid Haskell. And I think this has some cool properties, especially if you are into theorem proving and constructive proofs. So this has type, top right, is a model of refinement type checker. And to define it, we developed in Liquid Haskell something that we call data propositions, which is very similar to Cox inductive predicates. And yes, I think this is now the biggest Liquid Haskell proof that I know of, and we went to 10K lines of proof. But yes, we proved soundness of the has type relation, refinement type relation. And the cool thing is that, like the examples that I saw before, the proof is a Haskell function. Soundness, it recurses on what? So if it k-splits on the evaluation step, and yes, it k-splits on the evaluation step. If I just evaluate to myself, then it calls progress. If there is a step, it inductively calls itself with a smaller relation. Okay, so we proved it, and from this one could conclude that refinement types are sound. But yes. So in practice, Liquid Haskell is a refinement type checker, and we have more refinement type checkers, and the refinement type checkers are software, and the software have bugs. So Yes, the thing is that in Liquid Haskell and in Stainless too, on average, we get like 5 unsoundness reports per year, where an unsoundness report is a GitHub issue usually that says that a program was accepted by Liquid Haskell, but it violated the specification. So this is why it's unsoundness. It should have said no, and it said yes. And yes, like 5 unsoundness reports per year is kind of high for a verifier, especially if you compare with Coq or ROC now. That is a type theory-based theorem prover designed to be sound. And in Coq, they claim that they received about 1 unsoundness bugs per year, unsoundness report. Okay, so why is this the case? And the case is because Liquid Haskell implements a core, which is like the Lambda calculus that we mechanized and we believe that it's sound and we know exactly what's happening. But also it has many features that are like, because Liquid Haskell operates on GHC, on the intermediate representation of GHC, and there are many things that like we have not mechanized, let's say. And this is inference, coercions, GHC coercions, like fancy data types, and these are not part of our mechanized model. And also like the implementation is huge. The 400K is the implementation of Liquid Haskell, but we also trust GHC, we trust SMT, we trust a huge portion of the program. So the bugs, the unsoundness bugs, either rely on errors in the implementation that may happen by mistake, or by the logic that we don't understand very well. So in comparison, Coq has a tiny kernel, 15K lines of code. We implement CIC, which reduces to set theory. And set theory, like we have reasons to believe that is consistent, which means that CIC is also calculus of inductive construction is correct. So the only point that the like unsoundness bug appears is this 15K lines of code of lines of code that Coq trusts, the kernel. And actually, like there is a project that is trying to verify Coq in Coq to remove this source of untrustedness, right? Okay, and so the summary, like if you compare these two techniques, is that Coq is designed to be sound, while refinement types are designed to be practical. It is like we are attracting the same problem of verification, but from different perspectives, right? And like this is that Coq implements calculus of inductive constructions, which is a logic, while in refinement types we say, give me a programming language, and I am going to put logic on top of it. I'm going to put verification techniques on top of it. And because of this, because we work on an existing programming language and we care for practicality, the proof terms are implicit. And this means, for example, that we can the system can derive automatically that I is a safe index, or that 42 is a safe integer. It's a positive, is a natural number. While in theorem provers like Coq, all the proofs are explicit. You can do the same things, but you have to explicitly give a proof to prove the same properties that we prove. And yes, so with this in mind, like you have the soundness one side, you have the practicality on the other side, and like my vision, my goal is to somehow combine both of them. So you have a user that interacts with these practical refinement types of Liquid Haskell, Liquid Rust, or whatever other refinement type checker you want, and on the back you decode into a sound verifier like Coq, so you get both the soundness and practicality of formal verification. And with this, I would like to thank you for your attention.